There you go. It's all you.
Okay, good morning. Thank you. Sorry, the title I've been kind of tinkering with, so don't pay too much attention to it. Um, Basically, I was hoping to share with you some recent changes we've made with our HPC at GW, and then hope to have kind of a open discussion about what this can help with and what ideas people might have, and kind of go from there. And it might also help if people watch the recording later too. But anyway, let's go ahead. I don't want to dive. I'm trying not to do too deep of a dive into the minutia here, but um, uh, basically, I know some of you are pretty familiar with our HPC. Others may not be as much, but um, I think I'm going to skip ahead a little bit. Um, this is a little bit of an overview of what we have. Um, Actually, let's go here. So we have these main five clusters. So I want to give a shout out to Viper. That's pretty new. This is a small cluster, I think about 10 servers that supports the Open Science Pool, which is a inter institutional group that provides basically spare computing cycles to anyone with I believe the requirement is you need to have an academic affiliation. So, if you're somehow affiliated with a university as a student, staff, or faculty, you should be able to use Open Science Pool. So we have some older hardware that we I guess kind of donated virtually. So we still run it. We still all do all the system administrations work for it, but this is something that is kind of our way to participate in the larger community. Um, so that's Viper. We also have our main flagship research cluster, which several of you have used, Pegasus. Uh, that's about 200 nodes or servers. We use those terms interchangeably frequently. So we have Raptor, which is 10 nodes or servers, and that's kind of where we do testing. And we also have some researchers that found it useful to kind of run these um, corner case types of workflows. And I'll come back to that in a little bit. Um, but that's been useful for that scenario. And then we have Cerberus, which we've used traditionally. I think we've had it for 3, 4 years now. Traditionally, we've used it for in-class instruction. So, for example, Ali Ranavard in School of Public Health has a class that has some HPC elements, and they'll do like, I don't know, 2 weeks on Cerberus showing students how to get into it, access it, run some of their jobs, and then they move on to, other things. Some of the work they do is just local or maybe using cloud resources, so things like that. But it fits into that kind of teaching structure. Recently, we've also expanded it to do data science capstones, workshops, several other places that it's not the traditional classroom instruction, but it has been a good solution for that. Um, and that's about 20 nodes or servers. And then Gamoth is a dedicated physics cluster that we stood up, I think, 3 years ago, and that's used by the physics department. So that's again something that we help to support. I think they have a like a grad assistant that does some work on that too, but that's basically what that is. Um, so, all right, let's go back a little bit. HPC, why would you use it? When do you need it? Sorry, I know this doesn't match the slides. Uh, we use it it's useful when you have work that you need to do that exceeds what you can do on your laptop or your desktop, right? So something we're in the midst of working through is updates to our scheduler that makes it easier to compartmentalize jobs in a sense, or to filter them down to the exact resources you need. And that's something that really fits the non-classical, traditional, highly parallel types of jobs. So one thing we're finding is that the needs of our researchers are evolving over time. Of course, we have this whole AI boom, right? But even outside of that, we have over the past few years, we've seen people that are doing jobs that are just a little bigger than what they could do on their laptop. And so for those types of jobs, sometimes they would go out to the cloud, run things in Colab or other computing resources. But we have this supercomputer cluster, so we're always asking ourselves, how can we make this meet those needs better? Why can we use what we already have, right? Um, and so it really is a general purpose computing resource at GW. I hope that that is the takeaway, if nothing else, is that this is not only designed, we don't have this rigid requirement that you can only use this for, these classical super parallel MPI jobs where you're running across like 40 servers. That's still a valid use case, and we do have the researchers doing that, but that is kind of becoming the minority over what we were seeing. So we're also here to support local AI model type of jobs, people doing something with a little bit better resources than they have on their own computer, those types of jobs. So that's we try to make it do everything and anything as much as we can. So that's the idea here. So I want to get a little bit into what we are working through, and then I'll do some just some demonstrations in a little bit. Okay, now it's here somewhere. Sorry about this. Here we go. So there's a few ways of how do you get jobs to HPC? So we have the basic idea that we use is that you have many users and a smaller number of servers. So how do we fit those jobs into the tasks people are trying to do into a limited number of resources? Well, the traditional way has been with a job scheduler. And so you basically submit a job, you go into a queue, and then there's a process called dequeuing, which is how long does it take for your job to sit there and wait before it actually starts to run. Of course, as a researcher, you want to get your work done. You don't necessarily care that, there's all these other jobs waiting. You just need to get your results. And so scheduling has been a way to try to meet that need. Until we made this recent change, we were stuck in oh, I can't highlight when I'm in presentation. Hold on a sec. We were stuck in the node-based allocation format. There we go. All right. Sorry for my bad drawing skills. So this first one, node and queue-based allocations. The idea with this is that you would go in and we'll see it here in a minute. You would request, let's say you need GPUs. Well, maybe you need 4 GPUs or you need 2 GPUs. That's all available through different things called queues or partitions. And so researchers would need to keep all that in mind, like in the back of their head, what's out there, what can they use, and you also have to kind of have this working knowledge of um, how many servers are there that can support this type of job, and that's going to affect how quickly it can run because it's not a first in first out system. It's based on priority, and it tries to the scheduler tries to find available resources based on the request. So let's say you ask for 4 servers, that's going to be a harder request to fill than someone asking for 1 server. It's a very simple example. So again, with this node and queue-based allocation, that was restricted to just whole servers. Very much unlike what you see when you do most cloud computing. there is the traditional like go to AWS, you spin up an EC2 instance, and now you have your server, right? But a lot of the other platforms, things that are using Jupyter notebooks, for example, they will oftentimes let you select like how much RAM you need, how much GPU you need, and it's much more granular. That's what we are in the process of moving to. So that is what we call resource-based allocations. So it still uses the scheduler to manage everything. Um, we have not found a better way to do this. So it still schedules jobs. But the resource-based allocation allows you to do just what I was describing. You can say, okay, I know I need a Grace Hopper GPU and CPU combination, right? I need 1 TB of RAM. Maybe another job needs 50 gigabytes of RAM. You can select all those things, and I'll do a little demonstration of how that works. Um, so what this enables us to do is a lot of it really expands our capabilities. So it has drastically decreased DQ times. So that's important. Getting jobs to run faster is very, very critical. But even more than that, looking into the future, this allows us to do things like better support a condo model, where let's say a researcher has a grant or they have a startup fund, they can say, I have funds to purchase this nice server with 4 GPUs, uh, and it's going to be for my lab to use. Well, that's all well and good, but with the condo model, you can share that. So you can basically make it more of a university resource, but allow for better priority and preemption for your team. So, the person that kind of owns the system would get, first dibs on jobs. And if someone else is running something based on certain parameters, we'd be able to basically funnel, preempt that to allow the like the original research team that purchased the server to come in and run it, and where ahead of the other job. So where the resource-based scheduling fits into that is it allows us to be more granular with how that works. So we can say dedicate one of the GPUs to the original team all the time, and then the other three might be available to the bigger community. And much other, that's just a quick example. There's other ways you can do it. But with this support now in place, we can do things like that, and we can also just better support these other types of workflows. What we were seeing with the older model is that frequently we would have researchers that were getting a whole node, a whole server, and they weren't utilizing anywhere close to even half of it, much less 100%. And the worst thing we can have in a supercomputer system is these servers sitting idle doing nothing, just wasting electricity. They're expensive, so let's use them, right? And so we're really excited about this, and I think a number of you have started using it and found it to be useful. But let's take a quick look at how it kind of works. There we go. All right, I think my little doodle's gone. Okay, so getting into the system, there's a few different interfaces. There's a command line access. And so that's kind of the traditional SSH model. We have login nodes, so you need to be on a campus network, which is usually eduroam or wired if you have, a computer with Ethernet. Um, and the other option is to go on VPN. Um, and so once you do that, you can use a terminal to connect to Pegasus, and same works with the other clusters. So you SSH, you connect, you get to a login node, and from there you can submit jobs. And I'll show you how that works here in a little bit. And the way the job scheduler does this is there's two main ways to submit jobs. There's interactive jobs where you can kind of monitor, look at what they're doing. An easy to grasp example, I think, is Olama. You can run an Olama server on a GPU node. That's an interactive job. And then you can send queries to it either with API or directly into the interface. Olama run, or just type Olama and start working with it. You can send your queries and watch the real-time responses. The other approach, which is more traditional HPC oriented, is scripted jobs. So in that model, using the same example, you spin up a Olama server on a GPU node, and you have a whole list of queries, training steps, whatever you're doing. You send all that over as a script, and it runs. You wait for your results, you get your results, and you have everything. So there's very valid use cases for both types of jobs. So those are both supported with command line interface. There's also come back to this. There's web-based interface that we support with the Open On Demand web portal, and this allows you to. It's all using the scheduler on the back end, but it allows you to do what look like standard interactive jobs, but they can have graphical components. So you can have RStudio, you can have Jupyter Notebook. There's a lot of other possible. Oh, sorry for the typo here. There's a lot of other possible options. But right now we kind of have the catch-all remote desktop. So you drop into that and you get a remote desktop, similar to what you would see with other virtual computing labs and other platforms, except that you're actually on one of the HPC supercomputer servers. So you jump into that, you get whatever's on it, GPUs, the amount of RAM, so forth, and you can do graphical apps, you can do terminal apps, whatever you might need there. There's the potential to add more applications to the web-based platforms. So RStudio and Jupyter run inside the server. So you're connected to this remote server in the cluster, and you're just interacting with Jupyter, running your notebook cells, or you're interacting with RStudio and doing RStudio stuff. And there's other options. So there's VS Code. There's other sites have done a whole plethora of things. MATLAB. The sky's kind of the limit, and it does take time to kind of test those, get them integrated. But we would love to hear from folks here and elsewhere, maybe people what would help them, because this really is what I view as a way to kind of meet people somewhat in the middle, to where we make HPC a little bit easier for non-traditional HPC users. And I hope it's helping in that regard. It's maybe not quite as frictionless as some of the some of the cloud platforms, but it's kind of the best there is right now for getting that HPC infrastructure that an institute already has, and try to make it a little more open to users.
Can I ask a quick question?
Yeah, of course.
Do all the nodes have the same setup for ODD?
That is an excellent question.
You have to pick.
Yes, but
okay,
you're right. That's I'll do a little preview here in a minute, but this actually can be customized quite a bit, and I've done some experimentation with our serverless EduCluster, and you can do things like filter down. Do you need a GPU? How much RAM do you need? So it can do all that. Additionally, you can have things like dynamic content. So it can, if you select you select a resource that's more scarce, it can adjust like the max time limit. So we can kind of integrate more dynamic policies through the Open On Demand than we can on the the command line cluster side. There's kind of additional control of what we can support, and it can take something. Let's say we normally have a maximum time limit of 14 days. So with interactive jobs, our kind of stated policy is 1 day, and it's a little hard to run interactive jobs for a really long time anyway. You have to go in and unlock your password all the time. It's not very user friendly, but that can be controlled through the web content that is in OOD. It has it's Ruby forms is what it uses. So you can have basically this kind of looks like JSON, but you have this coded syntax that controls how it works. So it's very customizable. And
But
I've only
if
touched.
I want my students to
Yeah.
use Jupyter notebooks,
Yes.
they can select any of like if they go to Cerberus, they can select any of them, or are there just certain ones that have Jupyter notebooks?
Yes,
You know,
that's yeah,
like
good.
make sure they choose the right node.
Right. Sorry if I got off track a little bit. It's all kind of part of the same.
Yeah.
Yeah.
It's the
So
same
it does.
question, just a
Yes,
different aspect
it,
of
it can. And that's something where we would probably want to work with you and make sure we understand your use case. But the main idea is yes, you can the application itself is available across. There's some nuance to like, do we want to limit certain options to if you have a GPU and don't, that kind of
Yeah.
stuff.
Okay.
And it will like load the, maybe it can load the environment for you based on that. But yeah, just at the root level, it's all supported across all the different configurations.
Okay, thanks.
Yeah, of course. So and then trying to check the time. We'll try to touch a little bit on future ideas if we have time here. Okay, so um for those of you who maybe, I'm sorry, wrong, maybe haven't seen it yet, I'm gonna do a quick. Just a reminder, yes, IT people have trouble with passwords too. Uh, maybe more trouble even. All right. So typically when you get in through SSH access, you're typically using a two-factor code as well. So that's the last code was. Okay, so this is a login node on our Pegasus cluster. And so our default way of looking at the resources is this giant list of servers. So in our older node-centric resource allocation, everything was let's do it this way. This will pare it down a little bit. Um, everything was handled through. It didn't help at all, did it? Oh no, sorry, I scrolled up too far. There we go. Everything was handled through the partition side of things. So people kind of used this as I like to use the Excel filter analogy. Like you have your Excel file, you go up to that top header row and you select like Q and you hit that and then you can uncheck all the Qs you don't want to see. Like that's kind of how I think of this. You so we have a lot, right? It's more than 20. And it's a lot to kind of keep track of. And that's well intentioned, but it's also misleading and confusing. So what the way this was working is people would say, let's go to the default queue, which is this guy here. And this is telling us we have 110 nodes or servers. Oh, sorry, 126 is the last column here. 126 nodes or servers that are part of the default queue. They can run jobs up to 14 days. And here's the list of the servers. That's a lot of information, especially when it's presented like 30 times. So that's we're moving we're going to collapse this so that it's mostly CPU. And think of that as, non-GPU type jobs in GPU. And we'll have a few specialty ones as well. So Superchip is our Grace Hopper nodes. That is always going to be somewhat separate because it's a different architecture and it requires different codes and so forth. Visualization Viz is for these visualization nodes. Again, that's a bit of a different workflow, so we'll probably have that separate as well. But yeah, the idea being that we don't it's not really intended for researchers to need to keep track of all these different queue names. So the idea being, so here's one that was kind of a special case previously, high memory. Um, This is for users that know they need like a terabyte of RAM or 2 tera, up to 3 terabytes of RAM, which is 3,000 gigs roughly. Quite a bit of RAM. And you may have heard it's very hard to get now with memory being more scarce. So um, this previously this would be, you'd have to know you needed this high memory. You'd have to ask for it separately. It was kind of a not very not very logical or user friendly. So now using this new CPU system, the high memory nodes are actually here too. They're here in this last second to last spot in the list. And so instead, you can just say, I know I need 3 terabytes of RAM. I don't care that it's high mem. I don't care what you RTS guys name this. I just need 3 terabytes of RAM. So that is, we think, a little more flexible, and it also handles the resources better because you can now say, like, I need 2.5 terabytes of RAM. Well, that leaves the other 500 gigs, other half of a terabyte, for another job. So it's moving the kind of the onus on researchers needing to know like these kind of arcane Q names to just needing to know what resources you need. It may seem like a no-brainer, so I don't mean to belabor the point, but it's like, yes, I just want to make sure that comes across. So this is also touching a little bit on the future, I think, is that hardware is getting harder to get. Yeah, the AI players are getting a lot of the cool GPUs and high memory nodes and all these other things that traditionally we liked to have for our researchers. And so using this model, we're able to much more efficiently use the servers we do get. And, let's say next week, a server falls off a truck and we're able to grab it. We can support it much better using these more granular resource options than in the past. So yeah. So a quick example of let's just do a quick example of a job allocation. So previously, if we said we need high memory and we need 30 minutes, that's the time parameter here. This is what you would need to do to get an interactive job using the old mechanism. And it would need to find one of these high mem servers, and it would give you the entire thing, all 3 terabytes of RAM, all of the 40 cores, regardless of what you actually need to use in your job. And that would kind of exacerbate the long wait times. And so what we actually support now, and by the way, if we scroll up a little bit, we can see the high memory is actually all fully allocated, so we can't do it anyway. So what we support now is instead saying CPU and mem like 3000 G. Whoops. Let's use a different example. So 2500 G. This is telling the scheduler that we know we need 2.5 terabytes of RAM, and I don't care where it is, what it's called, just that's the resource I need. And then it will try to go and find it. With batch scripted jobs, it works the same way. You just put everything into a script. So I have some very nasty, terrible script examples. I leave a lot of things that are just kind of one-time, one-off things and then come back to them later. Okay, so well, here's an example of the new system. So we have this script, and all these lines are telling our job scheduler what parameters we need, what resources we need. And these last two are commented out, so we can ignore those. What we're telling it is create some output file, an error file if we need it. I'm asking for 30 minutes of time. I know I need a GPU, so I'm using the GPU queue. And this is the GPU I need. I need an L40S, and I just need one of them. And that's all it needs at the basic level. And what we'll see in a little bit is that the Open On Demand web interface kind of encapsulates all this or obfuscates it away and abstracts it away, sorry, in a kind of behind the scenes. So we're not saying like I need this weird queue name that I memorized and give me that whole node. This is saying I need a GPU and give me the default RAM and the default number of CPU cores, which is 1 and 4, I think, at this time. One core and 4 gigs of RAM. So and you can make this more granular. You can ask for more restrictive parameters. Again, I like that spreadsheet analogy that you're going into the filter and you're taking the entire list of servers and you're kind of filtering down to what you think you need very, more exactly. So, and then it's just running this command, which is again kind of a silly example. It's just checking what is the actual GPU. Um, so let's jump over to on demand. Oh, we're actually rolling out an update to this in the month of May, which you'll actually see here in our splash screen. So up here it says, yeah. That is something that will give us some new features. One of the features I'm hoping we can get, haven't actually been on the new one yet to test it, is it should give like a status page where you can see like what jobs are running and what's going on the system that we don't have with our current version 3.4 support that. So we're excited.
Yeah, we're still on.
Yes.
CJ.
Okay. Bear with me here. I do my handy connection test to Google. They have a very easy to remember IP address 8.8.8.8. If you haven't, yeah. If that comes back nothing, I know I got a problem. All right, it's reconnecting. Bear with me. Page updated?
No.
No. All right, let's try stopping and resharing. There's a joke here that we are better at running, my team's better at running like big server.
Ryan, you're muted.
Oh, yeah, I was. So the owl must have died too with that. So that's why I was muted. We're fixing tech issues. It keeps booting him out.
If you'd rather, I guess you could hook it up, but yeah.
But I don't have your term. I guess, yeah, you would have to SSH back in and everything, which would be a pain.
Maybe it's the wireless. I don't know.
Nope. Yeah, and it was working so well. You have your VPN on?
Yeah.
Do you have to for any reason?
Yes. The terminal. Well, yeah.
Okay. From on campus?
For the wireless.
Like I don't turn it on when I'm on campus. I only use the VPN from home. So if it's giving issues, but I don't know if that will fix anything. I just don't use it on campus. So.
We have to for some of our systems, but that's it's just kind of a habit. Okay.
You're gonna do interpretive dance. Great, James. Yeah.
Like many things.
So that's what an SBatch file looks like, an interpretive dance. That's exciting. Oh yeah. You missed a very nice SBatch dance.
That might actually be a good conference thing. Like whenever there's a tech issue, we've got like the dance students ready to just roll out, bring out the dancers, they entertain people until the tech gets solved, and they roll them back out again.
Well, I hear James, so that's progress.
Yeah. But we're not getting any wild feedback either.
Yeah, before I wasn't hearing anything.
Oh, there it is.
Okay.
It's coming.
Oh, there it is. Okay, it's doing
coming.
something. All right, so sorry about that. Let's try this again. This interface, they call them cards. You have these little clusters that, we haven't done it for Gamow and Viper. Viper is really external users for the most part. And then we've got the Jupyter in our studio option. Did it update when I clicked? Is it showing something new?
Yes.
Okay.
I see your desktop options.
Okay, cool.
Use all that.
Like the different types of things we have, and then you can specify different resources, how many minutes, how many hours, you can switch back and forth. I don't know how useful that is, but this is all stuff we can customize. So again, we can we're looking into having like under servers, there would be like a VS Code where you would run that directly on whatever allocation you have. So let's say you needed a GPU, you would select that, and then in the code web tab, you'd basically open a new tab in your browser. You'd be able to go and use Torch or whatever library you want to use. So that is and then same with this just opens a new tab, and it's running something there. So it's fairly user friendly, does away with the command line stuff, but it is that different that different use case of you need an interactive job. This really fits that scenario that you need something a little bit better than your laptop, but maybe not crazy parallel runs across all these different servers. Yeah, so it's just the old classic Jupyter, so it's not too fancy, but this is actually on one of our HPC nodes, so that's what it's doing. These are not my files. This is what's on the remote system, and then you can go and do things. So yeah, we're always looking for feedback of what would be cool to have here. Maybe something like Comfy UI could be integrated. There's different options, and just something we have to kind of spend the time to set up. So if it's useful, we're happy to take suggestions and work on that. And then of course we'll still have the terminal based system there to use going forward. I think it's just going to continue being a hybrid general purpose HPC platform with very different workflows over the next few years. So yeah, I hope people were we got a few questions, but yeah, if there's more questions, happy to allow you to jump in and ask them.
Yeah, I guess I can also show, I don't know if they can hear me, but
Should I stop sharing?
yeah, if you stop sharing, I'll show my workflows for this. Which is one of the reasons that I invited him to come chat with us too, was so this is some code that I have that it's a daily cycle, so I want this to run every day. Oh, how do I get rid of that?
Oh yeah, I've run into that too. Maybe escape? I don't remember.
Yes, get back to that.
Yeah.
Okay, so this is, I have an orchestration folder within my scripts, and this is the daily cycle. So it names it, calls it, it's a prediction market cycle. So this is running 300 agents in each market every night. And I tell it to do output files as logs to say what happened. And then those get saved over my logs files somewhere over there. And I used to say, like, I wanted, well, the first one runs on just GPUs. Because this is a fairly light script that just is setting things up. It doesn't actually require GPUs. So I just take 4 GPUs per task and just minimum 16 gig of memory. And I set it to run for up to 12 hours because this runs the whole time that the job is running. So if any of the jobs fail or have issues, then I have to have this part of the script wait. So I have a long run on it. And then I tell it not to requeue type of things. One of the things that Joe helped me with early on with this, I think, or at least he confirmed I could do it, is within them, I also then set up for the next daily run. So if you're doing something that requires, like, it runs at 2 a.m. and then I wanted to set up the next run at 2 a.m. And the easiest way to do that was just to build this in. So it actually writes the next S batch for 2 a.m. the next day to run itself over again. And so I guess if I go down to my terminal, I froze. I'll go back, but it works fine. So you can restart other ones. one of the things it does is like it loads Python, it loads a couple other things. And yeah, it pulls some environmental files. But it also then launches my bigger job one, which is my agent batch. And this is actually where all of the agents get spun up from. And so for this one, you can see now I'm asking for a GPU partition. After some playing around and lots of chatting with ChatGPT, I ended on the B100s as being the best GPUs for what I'm trying to do. I'm only doing 16 gigs of memory on each of them. And that's, again, after I've tried with more. And you kind of want to figure out like which ones actually run and then like play with lower and see if it still works or if it crashes and then go higher. But you don't want to pull like 32 gigs of memory if you're not actually going to use them, because then you'll wait in queue longer. So this is kind of the minimum. I tried 8 and it froze up all the time, so that didn't work. And then I did something with the n tasks per node. Again, ChatGPT told me to do it. But then actually what I do that I think is interesting is you can array out. So you can run 19 of the jobs at the same time, basically, or 20. Ever how many, I had to look up, I think actually we have like 24 GPU V100s or some other number, but I only took 19. So I have my 300 agents, I divide them by 20 so that each one of those 20 is getting just a limited number of agents it has to run. And then it runs those. So yeah, that's kind of how, like, if you want to set it up for file type runs rather than going through the open on demand, it's not really that hard to set it up so that it can do, again, I was looking to do nightly runs and use a fair amount of resources. So that was how I set mine up. And then within the S batch, it just tells it what are the things it's doing. So those 20 things they call shards, or I called shards at least. And that's each of the different shards then runs whatever 300 divided by 20 is, that number of agents are in that shard and they get run separately on the nodes. So, and then they run Olama in each of them. And they run multiple different Olama models, so there's a lot of complexity there that I won't share. But the main thing I wanted to share was just how you can really set this up pretty easily to run pretty complex things. And I'm happy to share any of this code with people if they find it useful.
Yeah, that's there's a lot of great data out there from like Chad and Claude and so forth. They have good so like they've seen a lot of scripts, right? So
Yeah.
they have pretty good parameters. Of course, you'll still need to dig into like how does it work on at GW, because Chad doesn't know what's at GW, what are all the different Pegasus nodes, and that's mostly because we have bad documentation, But anyway, it's yeah, that's a great point. Like you can get a lot of really good tips. It's their documentation's all freely available online. The vendor that makes Slurm, our job scheduler. So yeah, there's lots of little tweaks and flags you can use that can help with your job. So that's yep.
Yeah,
Useful
they
tip.
have quite a few different ones, some of which we don't implement. But it seems like
Right.
95% of them we implement. There's just a few that it said to try and then it
Yeah.
didn't work. And I emailed someone on your team and they said, yeah, we don't accept that.
Exactly. Yeah, that's where we can help, is to bridge the gap, is where there's something that's not clear how it works. And then we'll look it up and say, maybe we know how this works. But that's we have all that.
Yeah, but I was thinking like it might be of interest to some of your students, James,
Mhm.
that are getting more into it. Like if they want to run something that pulls different data every day to create different images or something, they could set it all up once and then just get the output files over time. Like if they were trying to do something creative that actually was dynamic based on
Oh, that's
news events or something, they could do that, not have to every morning wake up and hit the buttons again to get it to go,
right.
which is nice.
Definitely.
Every now and then you'll get a failure email, like in one of them, you can put in the email you if you get a failure. And then every now and again it will fail. And typically it's like one of the GPUs just got stuck on something and cycled and never finished its job. And so then you just clear that one and it finishes up everything else.
Yeah, there's some fancy stuff you can do, like make dependencies, so don't run this until this other thing's finished, and yeah, actually I think I'd seen that Thomas had already done some pretty cool stuff. But it's been a minute. Anyway, I guess we're out of time.
Yeah, well,
So-
great. So thank you so much.
Sorry for the snags.
Oh, no, don't worry.
Thanks, Joe.
Stop recording.
Yeah, again, hopefully the main takeaway is whenever you need help, reach out.